Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 5th, 2025, about 8 days ago. It introduces a framework that gives deterministic, provably sound probability bounds for large language model safety checks, achieving 6 to 8 times tighter probability bounds and spotting 3 to 4 times more high-risk instances than common sampling methods. The paper is titled BEAVER, an efficient deterministic LLM verifier. And as we will see later, the implications for verifying correctness, privacy, and secure code generation are quite significant. Figure 1 shows how the BEAVER verifier turns a prompt plus a semantic constraint into guaranteed probability bounds that a model response is safe. The left panels supply the ingredients, namely the prompt, the large language model, and the constraint. The central box depicts the token tree, which tracks partial valid sequences and their probabilities. On the right, the algorithm repeatedly selects and expands one frontier node, then updates the lower and upper probability bounds PLB and PUB. Table 1 lists sequences that rejection sampling drew for the safe bash command prompt. The table shows that only 4 distinct command sequences appear, even though the model produced many samples, which means computation gets wasted on duplicates. The probability column records how likely each full sequence is under the model. The sample count column highlights that safe commands like ls-al dominate the draws, yet a dangerous command starting with rm still receives non-trivial probability mass. Figure 2 shows how the token tree gradually grows as the verifier explores more partial bash commands, and how the probability bounds tighten along the way. The top left panel starts with only the empty root node, so the bounds stretch from 0 to 1. The top right panel adds first-level children like ls and echo, which already shrink the upper bound. The bottom panels illustrate expanding deeper prefixes, where green incomplete nodes spawn more branches and turquoise complete nodes lock in safe probability mass, driving the lower bound steadily upward. Table 2 compares how tightly different methods pin down the true probability that math answers are correct. The rejection sampling columns on the left show wide gaps between lower and upper bounds, because the method wastes many samples and still cannot localize the probability well. On the right, the BEAVER columns report much smaller gaps, often around 1 to 4 percentage points. BEAVER also converges in roughly half as many forward passes, so it is both sharper and more efficient. Table 4 reports how often models have risky output distributions for secure code generation, meaning the model has a non-trivial chance of emitting insecure code. The full table shows that rejection sampling labels only a handful of prompts as risky, while BEAVER flags roughly 1/4 to 2/5 of them. For instance, QN34B jumps from about 4% risky under rejection sampling to about 33% under BEAVER. The rightmost N columns indicate that BEAVER reaches tight bounds in roughly the same number of forward passes, so the extra risk detection does not cost much added compute. Table 4 showed that BEAVER uncovers many more risky prompts. Figure 3 now explains how it does so without extra compute. This figure compares how quickly BEAVER and rejection sampling tighten probability bounds for math correctness. A forward pass means one full, large language model evaluation for a chosen partial answer. The left panel tracks bounds versus the number of forward passes, and BEAVER's gap shrinks much faster. The right panel plots the same story versus wall clock time, showing BEAVER reaches tight, stable bounds far sooner in real seconds. Alright, the big takeaway is that BEAVER turns vague, sample-based safety checks into deterministic probability guarantees, often with 6 to 8 times tighter bounds at similar compute. That tighter view exposes 3 to 4 times more genuinely risky prompts, especially for privacy leaks and insecure code. Longer term, this kind of verifier could become a standard companion to any production large language model. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.